In the last separations class, I gave a review or a preview of the necessary concepts that you'll need to know from phase equilibrium. Today, I'll combine the principles of material balances and phase equilibria to design a flash distillation process. Flash distillation consists of a single process unit. So we also call this single stage distillation. And like all process units in chemical engineering, when you're drawing a process flow diagram, you can denote a process unit with a simple box. Into the single stage distillation unit flows a feed mixture, which is typically, but not always, a liquid. Out of the single stage distillation process are two exit streams, one vapor and one liquid. So traditionally, we draw the process flow diagram going from left to right, and because vapor tends to float on liquids because it's less dense, we draw the vapor product on the top and the liquid product on the bottom. And if we have vapor and liquid that are both coexisting together, we make the key assumption that the exiting streams are in phase equilibrium with each other. Importantly, they're in equilibrium with each other. The product vapor is not in equilibrium with the feed. We know that from last time that if a vapor and a liquid are in vapor-liquid equilibrium, in general, the compositions of the two streams will not be equal. So I'm going to start filling in this process flow diagram with some of the relevant process variables that we'll need. So I'm going to denote the vapor product composition as Y sub A. So this is the vapor product composition of component A. And remember, if we have a binary mixture, and most of the time in this class we'll talk about binary or two-component mixtures, I only have to specify Y sub A, because Y sub B is then obtainable by saying that Y sub B is 1 minus YA. So traditionally in separations, just to make it easier to keep track of things, we typically only talk about the more volatile component. Remember, the more volatile component is designated as component A. And XA is the liquid product composition of component A, again, of component A. So what other process variables do we have? Remember from material energy balances that in order to completely specify a process flow diagram, I need at least the amount and composition of every stream in the process. So we already have the compositions of our two products. We need a variable for flow rate of the two products as well. In MEB, we called this N dot or M dot all the time. And that is going to be a confusing notation for this class. So in order to clarify this a little bit, I'm just going to simply use the variable V for molar flow rate of vapor product. And we'll understand that V is the flow rate. It doesn't have to be V dot. So typically, remember in MEB, a dot above the variable signifies that it was a flow rate instead of just an amount. Similarly, for the liquid product, I'm going to say that the variable L is the molar flow rate of the liquid product. We need to do the same thing for the feed mixture. So for the feed, I'm going to say the variable F is the molar flow rate of the feed, and the composition of the feed is going to be Z sub A. In addition to these process variables, I need to also know what the temperature and the pressure is that we're operating the single stage distillation unit at. And additionally, if I am changing the pressure or the temperature, I might have some Q or W terms as well. So I'm just going to denote that with a stirrer and a heater for work and heat respectively. So now that we have our process flow diagram completely labeled, I next want to do a degree of freedom analysis to determine what information we would need to know in order to solve a problem like this. So start the degree of freedom analysis by counting the number of unknown variables we have. And to start, we'll only consider material balances. So Q and W are only going to be involved in an energy balance, so I'm not going to consider them here. Also, as a note, I drew this as a stirrer, but stirring the single stage mixture is not going to make it separate. So this is just an indication of some kind of shaft work that is changing. It's either pressurizing or reducing the pressure. And in general, I'll only do one operation or the other, not both at the same time. So in a single stage distillation, I'm either changing the pressure or the temperature while keeping the other variable constant, and then that is what is causing the mixture to evaporate. Remember, typically I say that feed mixture is going to be liquid, but it doesn't have to be. So the number of unknowns that we have is going to be the feed flow rate, feed composition, temperature, pressure, flow rate, composition, flow rate, composition. So that is 8 unknown variables. How many equations do we have that relate these variables? Because I have 2 components, I have 2 material balances, always. And because I have specified, or I'm assuming that my outlet compositions are in vapor-liquid equilibrium, I have 2 equilibrium relationships. So my 2 material balances are component A and component B, because it's a binary mixture. If there were 3 components in the mixture, then I'd have 3 material balances. If there were 4 components, there'd be 4 material balances. And minus 2 phase relationships. And the 2 phase relationships are again for components A and B. All right, and that is all the equations that I have, unless I have some additional process specifications. But absent any problem statement, this would be all that I would know. So there's 4 degrees of freedom here. So what are my options for things that I can set in order to solve for the other 4? Well, typically, if we're doing a separation, we at least know what the feed mixture is and how much of it we have. So typically, for separation processes, we're always going to assume that the feed is known. So typically, you know F and Z are known. So that reduces my number of degrees of freedom to 2. So I have to specify 2 things. And if I further consider what Gibbs phase rule says, remember Gibbs phase rule is 2 plus the number of components minus the number of phases, minus the number of reactions, again, but we don't consider reactions in this class. So for a binary mixture in vapor-liquid equilibrium, I've got 2 plus 2 minus 2 is equal to 2. But my options for Gibbs phase rule, remember, are T, P, X, and Y. And this is why I've defined the variables like this, right? So of my options of the 2 unknowns, after I specify what F and Z A are, 2 degrees of freedom, I have to specify 2 out of these. In other words, I cannot specify L and V and have a completely specified problem by Gibbs phase rule. So importantly, this tells me that if I specify what the temperature and the pressure is of my single stage distillation, then theoretically I could calculate what my exit compositions would be of my vapor and liquid products. And then by a material balance, I could calculate the amount of product I would have as well. So let's go through now and derive general relationships for what these 4 equations are. I said there's 2 material balances, 2 phase equilibrium relationships. So what do those look like? Remember, for my material balances, it's oftentimes easier if I start with an overall material balance. So I said component A and component B, but I can also do an overall material balance. So I can say what comes in is equal to what comes out. F is equal to V plus L. Neglecting that there's not a reaction, so generation and consumption are 0, and I'm assuming that I'm at steady state, so no accumulation. So F is the molar flow rate in, V and L are molar flow rates out. I've got in is equal to out. And this is an O, so I like to write my equations by giving some indication of what it is. So this O is for overall material balance. This A is for component A material balance, and I can get to that by multiplying the composition of the feed. So ZA times F is equal to YA times V plus XA times L. So these are my first 2 equations. These are my 2 material balances. And then just parenthetically off to the side, I'll write my component B material balance, but recognize that this is not going to be an independent equation. So I can't use all 3 of these. I can only use 2 out of these 3. And typically the overall and the component A balance are the easiest. So I'm writing this on component B, so instead of writing ZB, I'm going to write 1 minus ZA, because that is ZB, times F is equal to 1 minus YA times V plus 1 minus XA times L. And we'll only use that if we need it or if it's somehow easier to solve for than the others. But just by looking at it, you can tell that it's a little bit longer and therefore more difficult to solve. My two-phase equilibrium relationships are my Raoult's law for component A, which is YA times P is equal to gamma A. And again, we'll neglect this for ideal mixtures, times XA times PA star. And my Raoult's law for B is 1 minus YA times P is equal to gamma B XB PB star. All right, so this is the theory of flash distillation. In the next video, I'm going to solve a practice problem, and I'm going to show you that as the engineer, you are going to have the freedom, or you will have to specify what temperature and pressure you want this single-stage distillation unit to operate, subject to whatever goals of the separation you have. So typically, when you're designing a separation, you have some type of goal for purity of a product that you'd like. So if you specify that, that would enable you to solve for the temperature, the pressure that you should run your single-stage distillation. And what we're going to find is that there's going to be a trade-off in most of these single-stage distillations. So very rarely will you be able to do a perfect separation. In other words, I can't get pure component A in the vapor phase and pure component B in the liquid phase. So we're going to have to make some compromises. And typically, the more pure product that you desire, the less of that product that you'll be able to obtain. So as the engineer, you kind of have to choose what it is that you want in your separation and then design the separation in the most efficient way to make that happen. So that's all for this video. Practice problem is coming up next.